Hello everyone, welcome to SPSVERSITY. I'm here, your chemistry educator. A very good afternoon to you all. Hope you had your lunch and ready for the class. So if you like the videos by SPSVERSITY, I always request you to like the videos and also subscribe to the channel. And if you have any feedback or the suggestions, you can always put, whether it's positive or the negative comment. We don't mind. We always try to give our best. So put your comments in the chat section. Okay. Yeah, here we go. So in the previous class, I was discussing about the rate of the reaction. Whenever we say the rate of the reaction, that it's defined as the change in concentration over time. Let me just have a quick look that is there anyone who is watching? Okay, just give me a second. Yeah, I can see. So no one. Yeah, here we go. So in the previous class, I was saying about the rate of the reaction, which is equal to change in the concentration divided by the time which is taken for that change. And then there are different theories to explain the rate of the reaction. And in the previous class, we already discussed about how the change in the concentration is going to affect the rate. When you increase the concentration of the reactant, since the rate of the reaction is directly proportional to the concentration of the reactant, the rate is going to increase. And about the second thing, it is the effect of the catalyst. Whenever you add the catalyst to the catalyst for any reaction, the catalyst decreases the activation energy required for the reaction, thereby increasing the rate. More number of reactant molecules will possess that activation energy, which is lower, and then they can form the products. Now in today's class, we are going to see the collision theory, which says that whenever there is a reaction happening in a reaction container, for an example, the reactant molecules are going to collide with each other. Whenever they collide, the collisions may be successful or may not be successful. What do you mean by successful? Or it is also called as effective collision, or it is also called as fruitful collision. So what do you mean by effective collision? I can take a general example you might have seen in movies. So a hero can go and kick to anyone, or have a dash collision with anyone and everyone. So all those will not lead to a love. So when he meets a heroine, when they have a collision, and then that's how the story starts, right? The same way, the reactant molecules, I just gave a general example and don't apply it for the exams. Your teacher may not like it, and that will be awarded as 0. So whenever the reactant molecules are going to come and collide, definitely there will be collisions, but they may not form the products. If the products are formed because of that collision, then it's called as effective collision. And there is something, whenever we say the effective collision, or which is called a successful collision, there are two factors. One is the colliding molecules should have the proper activation energy, and the second thing, they should have the proper orientation. So what do you mean by these two? We have already discussed about activation energy in the previous session, but say this is a graph where the reactant molecules are here and the products are here. So the reactant molecules should cross a barrier to get the products, and this height from here to here, this is called as activation energy. Now the reactant molecules which possess the activation energy, if they undergo the collision with the proper orientation, then only the product is formed, and that is called as fruitful collision or the effective collision. If they have any of these missing, then they are called as ineffective or non-effective or unsuccessful collision. For example, if you take the example of hydrogen and the iodine, you can see here, say this is hydrogen and this is iodine. When they combine, you get two Hi molecules. So if they are going to collide this way, this collides with this one, but there is no collision between this and this particle. Can you see that? So this will be the way how they are going to collide. And this, because of this collision, there is no proper orientation and the reactant molecules separate as they were before. This is not called as a successful collision. This is called as unsuccessful collision. On the other hand, if you have the reaction like this, can you see in the second image? In this particular case, say this is one iron, this is one iron, this is one hydrogen, this is one hydrogen. They are going to collide this way, in a proper way. So whenever this kind of collision happens, all the molecules which are the combining molecules, they come closer and they collide in a proper orientation, resulting in the formation of successful collision. And you can see that the reactants are not going to separate as they used to separate in the before one, but they form the products. Okay, so the orientation plays an important role, and as well as the activation energy. So we have the rate is equal to P into ZAB into e to the power minus EA by RT, where this rate is proportional to, so rate depends on the effective collisions, that's the orientation factor, as well as the collision frequency. What exactly is collision frequency, which is denoted by the letter Z? Say A and B are the reactant molecules. The collision frequency indicates, say you have taken this the mixture of A and B in a container. So in unit volume, if you take the unit volume of that container or the reaction mixture, what is the number of collisions happening per unit time or per second? So in a reaction mixture, in a particular volume, say unit volume 1 cm cube or 1 dm cube or 1 meter cube, so in that volume, if you count the number of collisions which are happening per second, then it is called as collision frequency. So rate is equal to P, that's the effective collision times the collision frequency, into e to the power minus EA by RT. E to the power minus EA by RT is equal to, this is the fraction of molecules having energy more than or equal to activation energy. Say you have 100 molecules in a system, and out of this, say 25 molecules will have the activation energy or more than activation energy. So what is the fraction? It is 25 by 100. Okay, this is the factor which is given by e to the power minus EA by RT, where EA is the activation energy, R is the gas constant, and T is the temperature. Okay, so let's move on to the next topic then. Hope it's very clear to you. If you have any doubts, definitely you can comment it in the chat section. Okay. Then this is Arrhenius equation, which relates rate with the activation energy, or a rate constant, where K is the rate constant, which is equal to, so the rate constant of any reaction, that's directly proportional to the fraction of molecules which have activation energy or more than amount of activation energy. So more is the number of molecules which possess the activation energy, more will be the rate. Just for an example, so in your college or in your school, in the grade 12, you have sections A, B, C. You have the different sections, imagine this way, and more studious or more studious the students are, say class A, I'm just taking, I don't have any more affection on a grade the section A, say A students are very studious. And what do you think about that particular, how can you connect that with this? So A student, the grade or the section A students will have more energy or will have more knowledge, so they'll get good marks. So the success factor of that particular section A will be more. So more is the amount of energy possessed by them, more will be the rate of the reactions. How is the rate of the reaction, or the rate constant is related to this? K is directly proportional to e to the power minus EA by RT, or we always say that as K is equal to 8 into e to the power minus EA by RT, where A is called as the Arrhenius factor, or it is also called as pre-exponential factor. In the previous one, if you consider this, which is related to this one, the orientation factor and the PZAB, the activation energy, so this Z is the frequency factor, which is denoted by A over here. Okay, so whenever you consider a particular reaction, there is a particular value for activation energy as well as for the A factor. Now on changing the temperature, so if you increase the temperature, this is the effect of temperature on rate of the reaction. How are you going to predict it? So whenever you increase the concentration, whenever you add the catalyst, the rate of the reaction is going to increase. Now we have to see how the activation energy is going to be affected when you are going to increase the temperature, or how the rate of the reaction is going to change when you increase the temperature. So let us take a general example over here. What is going to happen here is, yeah, I'll draw the graph, one more graph over here. So this is at low temperature. This is the number of molecules with a given energy. This is a fraction of molecules possessing the activation energy, and this is a energy. This is a fraction of molecules. Then this will be the graph. What do you mean by this? That means let us consider this is a passing mark. Say the passing mark is 100. So this is the activation energy. How many students have this energy? Only those who can go through this, these many molecules will have the activation energy. That means if there are 100 students in the class, if only 25 students can score or can pass, get the pass marks in the exam, then this is that fraction, the fraction of molecules having activation energy, and this is the activation energy. So there will be molecules below this curve, but only those molecules which cross this line, which is equal to 100, they can form the products. This is at a temperature, say T1, which is a lower temperature. Now you increase the temperature. This is like the teacher is not pushing you, the parents are not going to push you to study during the exam, because of which what happens here, only this many students are going to pass in the exam. The temperature is low, the pressure is low, so the teacher is not going to beat you anything. And if the temperature, I'm just giving an example, so if the temperature is increased, or if the pressure on you, the temperature and pressure, don't get confused with the pressure, actual pressure. What I'm saying is relate the temperature to the pressure which is provided to you to score good marks. Say your parents are going to push you, like you have to study, you have to get good marks, and the teacher is going to give you a lot of assignments and the tests. So what do you think is the number of molecules which possess the activation energy? Because of that, there will be double the molecules which possess the activation energy. Can you see that? The area under this is more. Before it was only this much, now it has been doubled. So with an increase of temperature, the fraction of molecules, what is increasing? The activation energy is still the same. Can you see that? It's 100 only. The fraction of the molecules which possess the activation energy is going to double. The area under the curve is going to double. Because of which, what is going to happen? The probability of the molecules having activation energy is going to increase. So there will be more number of effective collision leading to the formation of the product. So always with an increase in 10-degree temperature, the rate is going to be doubled because of the same reason. Hope you get it. So we have from Arrhenius equation that K is equal to A into e to the power minus EA by RT. We have to simplify this and apply this at two different temperatures. Now, if you take the ln on both the sides, ln K, which is equal to ln A, this minus the power e to the power anything that comes, because ln is always base E, which is equal to 1. So this is minus EA by RT. If you change it to log, then what you have to do? You have to multiply the whole equation by 2.303. Then you have to divide the whole equation by 2.303 so that you're going to get this value. Let me take this one first, and now, or we can even take this one for the simplification. So at temperature T1, what is going to be changing over here? The A and EA values are fixed for a particular reaction. So the rate constant is K1, which is equal to log A minus EA divided by 2.303 RT1 at temperature T2. This is a different temperature, say the higher temperature. Then log K2, which is equal to log A minus EA by 2.303 RT2. Now, what we are going to do is log K2 minus log K1, which is equal to, when we change it, what is that we are going to get? Log equation 2 minus equation 1, that's log A minus EA divided by 2.303 RT2 whole equation minus log A minus EA by 2.303 RT1. I hope you get it. Now, log A minus log B is log A by B. So it's log K2 by K1. Log A and log A terms are common, so they get cancelled. So this is minus into minus becomes plus. So in these two terms, EA by 2.303 is common. So I'm going to take EA by 2.303 R is common. I'm taking it out. So it is 1 by T1 minus 1 by T2. You can also write this expression as, this particular expression, you can also write it as log K2 by K1, which is equal to EA divided by 2.303 R. You can take the common denominator, that is T1, T2, in the denominator T2 minus T1. You can apply any of this, and you have, if you just want the value of activation energy, knowing if any one rate constant value and a particular temperature is given, then if you have to find out EA, you have to go for this expression. If you are given with two different rate constant at different temperature and you have to find out EA, you can go for this expression. So how do you draw the graph for this? So you have to find out the A value. Then you can't go for the last expression because the last expression doesn't contain any A term. If you want the A, that's a pre-exponential factor, then you have to go for this equation. So if you're going to plot a graph in this particular equation, I'm changing the color of the ink so that you get to know where I'm writing. So if this is in the form y is equal to mx plus c. So how would be the graph? Can you see that? It can be log or ln depending on the expression. Ln k and 1 by t if you are taking over here, you are going to get the slope of the line as minus EA by r. If it is log term, then again it is going to change. The 2.303 gets added. Oh, so the intercept of this line is going to give you the ln A factor. So if you convert it into log and take the anti-log, you're going to get the A value. So in this particular topic, we have studied what exactly rate and how to write the rate expressions, what exactly is molecularity, what is order, what are pseudo first order reactions, and how to determine the rate constant equations for 0 and the first order, and along with that how the concentration, temperature as well as the catalyst is going to affect the rate of the reaction. Now let's move on to the MCQ section, which includes the couple of MCQs from all the topics which are mentioned over here. So go ahead with this. So I want you to, if you are looking at the videos, please answer this. Yeah. Yeah, there is no answer. There is no answer for this. So we'll go ahead with the answers. Rate of the reaction is defined as decrease in the concentration of the reactant, increase in the concentration of the product, change in concentration of any of the reactant or products per unit time. All the above three are correct. So decrease in the concentration, that's just a change in concentration, that's it. Increase in the concentration, that's also change in the concentration. How do we define rate? It can be with respect to the reactant or with respect to the product. We write change in the concentration divided by change of time or per unit time. So the correct answer for this particular question would be change in the concentration of any of the reactant or product per unit time. That would be the right answer. So we have the next question. 2A plus B gives rise to 3C. For the reaction, instantaneous rate of the reaction is You know that we have two different rates. One is the average rate, the other one is the instantaneous rate. Whenever you say the average rate, it will be the delta, the symbol you are going to give. This is over a period of time. And if you are going to mention this D, this indicates it's instantaneous rate. Okay. So how do you write the expression for this? Always the change in the concentration of A with respect to time will be equal to the change in the concentration of B. This the negative sign indicates their concentration is decreasing, which is equal to increase in the concentration of C divided by T dt. And here for the product you put a plus sign. Always for the reactants you put a negative sign, and for the product you put a positive sign, and the numbers which are found in the equation, they come down over here. So it's minus dA by dt, 2 dt minus dB divided by 1 dt and plus 1 by 3 divided by dC divided by dt. So option B would be the right answer. The rate of the reaction the rate of spontaneous reaction is generally very slow. This is due to the fact that so whenever you see the spontaneous reaction, these are the reactions which happen by themselves. But you have to initiate the reactions. Okay. So what is the answer for this? The equilibrium constant of the reaction is less than 1. The activation energy of the reaction is large. The reaction is exothermic. The reaction is endothermic. So the spontaneous reaction can be exothermic as well as the endothermic. And whenever you say for example, you take this reaction, reactants give rise to product. So this is a spontaneous reaction. How about the equilibrium constant? Equilibrium constant is equal to the spontaneous reaction need not be reversible, so we don't come across the equilibrium constant over here. But generally, for the spontaneous reaction, initially, when the reaction starts, you have to provide energy. You have to initiate it. You have to provide the energy which acts for its activation energy. Okay, so now say for crackers, you have the crackers for some festival like Diwali, where the crackers do not burn by themselves. So you have a chain of crackers, and from one end you have to fire it. You apply or you have to apply the fire so that the whole chain, the cracker chain, is going to um, burst out. So this is how the spontaneous reactions are. You have to start, you have to initiate the reaction. Whenever you have to initiate the reaction, you have to provide the energy. That means that energy is taken as the activation energy. So the activation energy of the reaction is large. That's why the option B is right. And once the reaction starts, it is going to proceed by itself. The rate of N2 plus 3H2 will be in equilibrium with 2NH3. In this kind of reaction, the rate of the change of concentration for hydrogen, they have mentioned it. And the rate of change of concentration for ammonia, this is what you have to find. So how are you going to proceed with this? Okay. So how do you write the rate expression for this? Minus the N2 divided by dt, as it is a reactant, which is equal to minus dH2 divided by 3 dt, which is equal to plus 2 dNH3 divided by dt. Am I right? No. This 2 should come in the denominator. Because this 2 should come in the denominator. Now, for the reaction, the rate of change of concentration for hydrogen they have given is minus. Why did they give the minus? Because it is decreasing. 0.3 into 10 to the power minus 4 the molar per second. So is anyone watching? Please like the videos, and you can put your answers down over here so that even I can appreciate your efforts. Yeah. So the question in this particular reaction, they have given the concentration of hydrogen, the rate of change of concentration of ammonia. So how do you do that? So you need only these two terms, ignore the other one, nitrogen we don't need. So minus dH2 divided by dt. What did they ask? the rate of change of concentration of ammonia. So we don't need 2. So you take it to this side, which is equal to dNH3 divided by dt. So when you apply the terms, they have given you minus 2 by 3. The rate of change of concentration of hydrogen is this one. So 3 and 3, it's, yeah, 0.1 now. So this would be, am I right? Are you looking at this? If you are, so this is going to give you 0. Minus and the minus, they get cancelled. 0.1 times 2 is 0.2 into 10 to the power minus 4 molar per second. So the correct answer would be plus. That's the option A would be the right answer. Hope you get the answer. For the reaction 4A plus B gives rise to 2C plus D, which of the following statement is not correct? Which is not correct? Yeah, what do you say? They have given the not correct, so you have to see that first. We'll write the rate expression. Rate is equal to minus 1 by 4 dA divided by dt, which is equal to minus dB divided by dt, which is equal to plus dC divided by 2 dt, which is equal to plus d concentration of D divided by dt. Now the question is, the rate of formation of C and D are equal. Are they equal? We'll see all the options available. The rate of formation of D, that's this one, is 1/2 the rate of consumption of A. And the rate of appearance for C is 1/2 the rate of disappearance of B. The rate of disappearance of B is 1/4 the rate of disappearance of A. So what do you think is the right answer? I'm waiting for your comments if you're watching. What do you think is the right answer? How do you find out the right answer? Which is not correct, that would be the right answer here. Rate of formation of C and D are equal. What is the second statement? The rate of formation of D, that's ddy divided by dt, is 1/2 the rate of consumption of A. Is it 1/2? No, it is not. The rate of appearance of C here is half the rate of disappearance of B. Is it true? The rate of disappearance of C, that's a dC divided by dt, is 1/2 the rate of disappearance of B. It's right. The rate of disappearance of B, this one, is 1/4 of rate of disappearance of A. This is also right. Rate of formation of D is 1/2 of the rate of consumption of A. 1/2. This would be the not correct one. In the reaction N2O4 gives rise to 2NO2. The pressure of N2O4 falls from 0.5 atmosphere to 0.32 atmosphere in 30 minutes. The rate of appearance of NO2 is. So how do you write the expression first? That you have to write minus d N2O4 divided by dt, which is equal to plus 1 by 2 dNO2 divided by dt. This is how you write the expression. After this, the pressure of N, this falls. So initially, the final one is 0.32 and the initial pressure is 0.5. This happens in minutes. We need the answer in minutes, so we'll retain that. So this is going to be minus into minus is plus 0.18 divided by 30, and this 2 comes over here. So it is 0.36 divided by 30, 0.0 0.012, if I'm not wrong, atmosphere per minute. So the correct answer would be 0.012 atmosphere per minute. In a reaction, K1 and K2 are the velocity constants for the forward and the backward reaction. The equilibrium constant is. So for a reaction, reactants give rise to product. So this is the forward reaction K1 and this is the rate constant for the backward reaction. So how do you put the equilibrium constant as? How do you write the rate for forward reaction? Rate is equal to K1 into the concentration of the reactant. For the backward reaction, rate is equal to K2 into concentration of the product. Then the Kc becomes equal to rate of forward reaction divided by rate of backward reaction. That's nothing but Kc is equal to K1 divided by K2. So the correct answer would be option A. We have the rate expression and we have to find out the order of the reaction. So how do we do? Order is the sum of the concentration of the sum of powers of the concentration products here. So if you sum them up, it is half plus half 1 by 3 plus 1. So can you see that? So if you add all of them, you take the common denominator, that's 6. You have only two options. So it is 3 plus 2 plus 6. So it's nothing but 11 by 6. So the correct answer would be option D, with order is equal to 11 by 6. So we have a balanced equation over here. That's PA plus QB gives rise to product. What is the rate? Rate is equal to K into A to the power M, B to the power N then. So from the balanced chemical equation, we won't be able to find out the order of the reaction. So we need the rate expression, rate law expression, from which we can determine the order of the reaction. So which is our rate law expression? This one. So the order of this is M plus N. This will be the order. So how do you define the order as? The order of the reaction is sum of the concentration terms, powers of the concentration terms in the rate law expression. This may or may not be equal to stoichiometric coefficients. Okay, so this will be P plus Q, which is equal to M plus N. This may be equal to or may not be equal to the stoichiometric coefficient. So the correct answer would be option D. So we have the next question over here. The rate law of for the reaction is given. Now what you are supposed to find out? So what do you think is the right answer? If you're watching, you can put the answer, random answer. If you don't know also, you can try your luck in the comment section. So the rate law for the reaction is, so they have given the rate law. On doubling the concentration of both A and B, so the reaction is of second order with respect to A and first order with respect to B. On doubling the concentration, what you are going to do here? You are going to double the concentration. In the place of A, you are going to take it as 2A. In the place of B, you are going to double the concentration of B as well. So this becomes 2 to the power 2 into 2 to the power 1. So the rate increases by 2 to the power 2 is 4 into 2, 8 times. So it is going to become 8x times. Oh, okay. Yeah, the next one. They have given a reaction here. The acetone, which is going to react with the iodine in the presence of acid, produces a product. The rate of is governed by, they have given the rate law expression. Rate is equal to K into concentration of only two reactants. The rate order of iodine is. So if you see the rate of the rate law expression, there is no iodine term. So rate is equal to K into concentration of acetone into concentration of H plus. There is no iodine term, isn't it? So what you can say from this? The rate is independent on concentration of I2. So with respect to I2, it is a zero order reaction. If the rate is independent on the concentration of that particular reactant, it is called a zero order. So varying the concentration of I2, that's a iodine, doesn't have any effect on the rate of that particular reaction. That's what we can conclude. Then we have the next one. So what do you say about this? The reaction is given 3 molecules of ozone undergo dissociation to give two molecules of ozone. They form 3 molecules of dioxygen. And the reaction proceeds in 2 steps. So one will be the faster step, the other one will be the slow step. So how do you write it? Always the order or the rate law expression is given in terms of the concentration of the reactants, which is the slowest step, O into O3. But do you have this one? Because O is the intermediate, this is the intermediate which doesn't come in the equation. So how do you write the rate expression for this? From this lowest step, you are going to take that slowest step as a reaction, from which you are going to measure the order. But from the first equation, what do you have? That's a equilibrium equation, right? So Kc, you can say Kc, the equilibrium constant, which is equal to rate of forward reaction divided by rate of backward reaction. So how can you put it? So it's O2 into O divided by O3, if I'm right. Then here, so how do you rearrange this for O? O is equal to K into O3 divided by O2. So in the place of intermediate, in this particular expression, you are going to apply K into Kc into O3 into O3 was already there divided by O2. This is what you substituted from here. In the place of O, you substituted this. So it is K into K is nothing but the, am I right? So this, okay, O into O3. So what do you say about this? K into Kc is nothing but the K, it's a new constant, O3 power 2 and O2 that goes to numerator, that becomes the power 1. So it's K into O3 power 2, O to the power minus 1. B would be the right answer. So in this type of reactions, where the reaction is going to be a complicated one, which has multiple steps, so from this lowest step, you are going to write the rate law expression. If you have any intermediate which is not appearing in the main equation, so take the reversible reaction from which you are going to find out the equilibrium constant, and from that equilibrium constant, you are going to find out the concentration of the intermediate species. Then you are going to apply it in the main equation. That's how you find out. For a reaction of zero order, so what is the expression? So zero order reaction is the one where the rate is independent on the concentration of the reactant. So you write minus dr is equal to k dt, or after integration what you are going to get, r is equal to kt minus r naught. When you rearrange this expression, what is that you are going to get? Kt is equal to initial concentration of the reactant minus concentration of the reactant at time is equal to T. So instead of R naught and R, you can always take Is this right? Do we have anything else apart from this? So option B and option C, they look the same. So I'll change one of the equations. So this should be A naught and A. So it's R naught minus R is nothing but A naught. The initial concentration can be taken as A naught, and the concentration at time t is equal to T can be taken as A. So for an endothermic reaction, A gives rise to B, the activation energy. We'll draw the graph. What is endothermic reaction? The reactant molecules have lesser energy than the products. So they take up this much amount of energy. And this is called as activation energy. So activation energy, so they have given you the activation energy as well as enthalpy change. The activation energy for the reverse reaction is, so how are you going to find it out? What is the answer? So in this particular reaction, what is this height? How do you find out? Enthalpy change, which is equal to 15. Do you get that? Enthalpy change is equal to 15 minus. So in this particular reaction, this is a threshold energy. This is the threshold, I'm sorry. Here in this particular reaction, how do you write enthalpy change? Enthalpy change is given as delta H is equal to EA, that's the activation energy, minus EA, this one. So 15, the enthalpy change they have given, enthalpy change of the reaction is plus 5, which is equal to 15 minus EA. Now, which is equal to, which gives you EA value as 10 kilojoule per mole. For the reverse reaction, this is the answer. That's nothing but 10 kilojoule per mole. Hope you understood this. That means, what do you mean by the reverse reaction? When this will be the reverse reaction. So the activation energy, before it was this one, the enthalpy was given, and now the activation energy is this one, enthalpy is this one. So this is how you calculate. This is for endothermic, and this is for the reverse reaction will be exothermic. For an exothermic reaction, the same way, activation energy is given, enthalpy is given, the activation energy for the reverse reaction. How do you find out? For this reaction, the enthalpy change would be EA minus EA. So they have told the exothermic reaction. So this will be minus because the enthalpy, heat is given out for exothermic. Previously it was positive because it is endothermic, right? So for endothermic reaction, change of enthalpy will be positive, and for the exothermic reaction, this will be negative. And they have given the EA value minus EA. So this will be EA for the reverse reaction would be 100 kilojoule per mole. So the correct answer would be option D. The rate constant of the reaction increases by increasing the temperature, increasing the concentration of the reactant, carrying out the reaction for longer period, adding catalyst. By adding catalyst, increasing the concentration of the reactant, carrying out the reaction for longer period, that cannot be the answer. Option C cannot be the answer. By increasing the concentration of the reactant and the addition of the catalyst, the rate of the reaction increases, but the rate constant increases by increasing the temperature only. So the next question. At 290 Kelvin, the velocity constant is nothing but the rate constant. at 298 Kelvin, K1, I'll take it as K1, at 300 Kelvin. At 300 Kelvin, when the temperature doubles, increases by 10 degrees, K doubles. So it's almost the double of that. 3.2 into 2 is 6.4 into 10 to the power minus 3. So the correct answer would be option B. An increase in the reaction rate as a result of temperature rise from 10 Kelvin to 100 Kelvin is. So this way, so if you have 10K, from that if you have to go to 20K, the reaction rate increases by 2 times. That's 2 to the power 1. 20 to 30, 2 to the power 2. 30 to 40, 2 power 3. 40 to 50, 2 power 4. So 10 to 100, it's 2 power 9. What is 2 power 9? It's 512. So the correct answer is, when you increase the temperature from 10 Kelvin to 100 Kelvin, the increase in the reaction rate would be 2 to the power 9 times. At 300 Kelvin, the rate constant is given. At 320 Kelvin, also the rate is given. So we have the expression log K2 by K1, which is equal to EA by 2.303 R 1 by T1 minus 1 by T2. So log of two values, 0.0693 divided by 0.0231. So this is almost 3 times log 3, which is equal to EA, activation energy, is what we have to find out. 2.303 into R is 8.314, multiplied by 1 by T1. The first temperature is 300 Kelvin and the second one is 1 by 320 Kelvin. So this is log 3. Then in the denominator you have 19, and then 1 by 30, 1 by 300 and 1 by 320. If you simplify that and if you find out the answer for this will be almost equal to 43. So the correct answer would be option C. The activation energy of a reaction is given. The increase in the rate constant when the temperature is raised from 295 to 300 Kelvin. So what do you say? What do you do now? You can always take this as log K2 by K1 is equal to EA, 9 kilocalorie per mole. I can take kilo, so 9000 divided by 2.303 into then R value you have to substitute. It's given kilocalorie, so the R value should be accordingly. That's 2, and the 2 here it is 21 minus T1 into T2. That's 295 into 300. What is the difference? That's 5 between them. So what's that you are going to get over here? So you are going to get 0.1104. That's equal to log K2 by K1. Then K2 by K1 is equal to anti-log of 0.1104, which is equal to, so how do you find it out? Anti-log 1.2. Now K2 is equal to K1 into 1.2. So the rate increases by 1.289, almost 1.3, by increasing the temperature by 5 Kelvin. A reactant A forms two products. A gives B, the activation energy and the rate constants are given. A gives rise to C, activation energy and the rate constants are given. If E2 is equal to 2 E1, then K1, K2 are related to. So how do we do that? So we know that E1 is equal to E2 is equal to 2E1. So how are we going to do that? We have K1 is equal to A into e to the power minus EA by RT1. K2 is equal to A into e to the power minus EA by RT2. They have given E2 and E1 values they have given. So I can always write E1 and E2. If E2, they have given two different reactions. For the same reaction, we have this expression. So A2, I'll write it as A2. Now, this is, I can write it as E1 and this I can write as E2. The temperature we can need not change because this reaction is not going to happen at two different temperatures. So they have given the different reactions. So what we do, K1 by K2 is equal to A1 e to the power minus E1 RT divided by A2 e to the power minus E2 by RT. This is what we are going to do, isn't it? Now, K1 by K2 is equal to A1 by A2 . What is A1 by A2? Into e to the power minus, this goes to the numerator and this becomes a positive term. That's E2 minus E1 divided by RT. Then what you are going to do with this? This is again a constant A1 by A2. I can write A e to the power E2 minus E1. In the place of E2, I can put 2E1. 2E1 minus E1 is E1 divided by RT. So it is K1 is equal to K2 yeah. So it will be K1 is equal to A into K2, this one. So you get A into K2 e to the power E1 by RT. So that will be the right answer. That's option C. The activation energy of two reactions they have given. The temperature is increased from T1 to T2. Rate constant of the reaction changes from K1 to K2 dash in the first reaction and K2 to K2 dash. So this should be, I guess, okay, K2 dash in the second reaction. Predict which is right. It should be K1 dash, I suppose. So we know that in the particular reaction, which of the following expression is correct? So what do you think? How do you solve this one? The temperature of the system is increased, the rate constant changes. That's K1 at higher temperature to K1. This will be greater than K2 dash divided by K2. Take log K1 dash divided by K2, sorry, K1, which is equal to E1 or EA divided by 2.303 R T2 minus T1 divided by T1 T2. For the other, you take log K2 dash by K2, which is equal to E2 divided by 2.303 R, then again T2 minus T1 divided by T1 T2. When you take the common denominator, they have given EA is greater than E1 or E1 is greater than E2. So what do you get after this? Log, I'll write it over here, log, you're going to the activation energy if the temperature is increased from T1 to T2. Yeah, then if you subtract this and if you simplify this, you are going to get the first one. This, since the activation energy for the first one is greater, its rate constants at a different temperature should be greater. So this answer would be the right one. Yeah. So I think the session is kind of clear to you all. So if you like the sessions, please click a